Hello dynamics students. For this mini lecture, we'll be looking at a conservation of energy problem for rigid bodies undergoing planar motion. This is a review problem taken out of chapter 18 from the 14th edition Hibbler Dynamics textbook. So for this problem we have a cylinder, I believe, or a disc, and that becomes important because it's rolling, and we'll need to know what its moment of inertia is. So we have a disc that's going to be rolling along its edge, and we're told that we can assume it's rolling, it's not sliding. So that gives us a relationship between its rotation and the translational motion of its center of mass. So that gives us a little snapshot of kinetics. And it's going to roll down the slope, and as it does, it's going to, of course, lose a little bit of gravitational potential energy, and it's going to stretch a spring. So we basically have three forms of energy to be concerned with in this problem. We have the kinetic energy, which we can think about as being divided into two parts: the translation of the center of mass and then the rotational kinetic energy. We have the spring energy, which will be increasing as we go, and then we'll have our gravitational potential energy, or we can think of that as the work of gravity. Gravity will do work on our disk as we move forward in the problem. So we're going to equate total energy initial to total energy final. Because what we're going to want to do is find what the total distance that the disk moves down the slope, and it continues, before it stops. And we're given some initial conditions. Initially, the spring is unstretched. It's in its neutral position, we'll say. It's also not compressed. Neutral position. And we know something about the motion. It has a speed of 4 meters per second. And so from this, we can say that our spring energy, we'll call it initial, equals 0. And our speed of 4 meters per second, we'll use that to get our, we'll call it kinetic energy of the center of mass, which is just simply 1/2 times our 40 kilogram mass. Times the velocity of the center of mass, which we are told is 4 meters per second. But we've also got some rotational kinetic energy. Because that disk is rolling. So in order to take account of that, we're going to use our rotational analog to our kinetic energy expression, which will be 1/2 times I disk times our angular velocity squared. So we can look up the moment of inertia of a disk in a handbook or in the back of our textbook, and we find that in this case it's for a 1.3 meter radius, we're going to end up with a moment of inertia in this case of 1.8 kilogram meter squared, and that is based on a 1/2 times mass times r squared equals I disk. Okay, and for a body that's rolling, we can use we can relate the point of instantaneous zero velocity to the velocity of our center of mass, which we know is 4 meters per second, and the angular velocity of the rigid body using our rigid body kinematics, and we can with the radius, of course, and we can get a value for our rotational velocity of our wheel, whose center of mass is moving at 4 meters per second. So the velocity of the center of mass is going to equal the radius, ends up being really simple, times omega. And so we end up with an omega equals probably the simplest aspect of rolling kinematics. Okay, now we don't have per se a value for gravitational potential energy initially. What we can do is say we can establish a vertical datum. Now, those of you who might be going into surveying know that that's basically a vertical reference point of sorts. So we can say that our initial gravitational energy, we can just arbitrarily say that U grav initial is, we can just call that 0. So if we call it 0, then we can say that we're going to lose gravitational energy as we go down. So we now have a pretty good statement for our initial state energy-wise. We can do a little bit of algebra and get a comprehensive total kinetic energy, combining our translational kinetic energy, the center of mass, and rotational, using I disk and omega. The spring's neutral when we're starting, so we know that's 0, and we've established gravitational potential energy as 0. So in our final state, we can do another energy tally, and we can say that our U spring will be equal to our spring energy, which is 1/2, times the spring constant, which is 200 newtons per meter, times the stretch of the spring. In this case, we can relate the geometry of the problem. As this spring stretches, the distance of the stretch is equal to the distance of travel of the center of mass of that disk downslope, which is in fact what we're looking for. So our max stretch will actually be our max distance of travel. So we can just call that d squared, where we can just write d equals center of mass travel distance. Okay, and we can use our slope angle to say our gravitational potential energy is going to end up being a negative mgh, where h is the vertical distance traveled downward, which is simply going to be our distance along the slope times sine of 30 degrees. That's 9.81 meters per second squared, and our mass is 40 kilograms. Okay, and kinetic energy final is 0, because we're told that that instant in which we've gone the maximum distance, at that instant the disk is at rest. Now it may roll back up the hill because we'll probably have quite a bit of energy stored in the spring at that point, and we'll probably do some kind of oscillating motion before it finally comes to rest in a final position. But we're just looking at its initial max position of max travel down slope. So we can equate that as the first place it stops. So now all we have to do is tally up everything on this side. This value, which is easy, is 0 plus 0 plus the sum of the two kinetic energies. So if we get values for each of these kinetic energy expressions, we can basically get a total value for the two combined. I won't work out all the math right here on our problem, but their sum ends up being 480 Newton meters, otherwise known as 480 joules. So that's going to be basically divided into the energy to stretch the spring minus the actual gravitational potential energy that we lose. So the gravity is actually going to kind of add to the energy that we had coming from the spring. So as it turns out, our gravitational potential energy that we lose, so the work of gravity done on our disk, ends up being 196.2 newtons times whatever that max distance we have. So this ends up giving us an expression in terms of d. So we can say this 480 Newton meters is going to have to equal the sum of this plus that. So another way of saying that mathematically, 480 Newton meters is going to equal, I'll simplify that a little bit, 1/2 of 200 newtons per meter. D squared is the same as just 100 newtons per meter d squared, minus, because we are subtracting gravitational potential energy, we're losing it. We didn't have to lose any kinetic energy to push something uphill. We're rolling downhill. So we have 196.2 newtons times whatever the downslope distance that we traveled that we're solving for. These two are equal. Over here we have energy total initial, and this is energy total final. So we're invoking conservation of energy. This is very similar to what we did with particle conservation of energy, with really the relationship between center of mass and rotational velocity, and the whole concept of rotational kinetic energy. Those are really the only departures we have from the energy initial final equivalency that we saw with our particle kinematics and particle motion. So all we have to do now is basically just take the 480 newtons to the other side, and we end up with a quadratic equation that we can solve. 100 newtons per meter d squared minus 196.2 newtons d minus 480 Newton meters. We can do a quick units check. We have a newtons per meter and we're going to multiply by a linear distance in meters. We'll end up with Newton meters, and then we have newtons times d will give us Newton meters. So we have consistent units. That's a good check. So you could call that A, B, C. Go through the quadratic formula, your favorite quadratic solving method. That's probably an easy one, but you can solve that and get a D of 3.38 meters. So this disk will roll downhill 3.38 meters. And the spring will stretch out. We'll consume all of our kinetic energy and some gravitational potential energy in stretching that spring out until we have energy equivalency with zero velocity, and then the spring will start retracting. It will gain both gravitational and kinetic. We won't come back as far because we'll be going back uphill. But anyway, that is how we get the answer to the question in Hibbler. Total energy initial equal total energy final. And probably the most challenging part is dividing up our kinetic energy into translational of the center of mass and rotational. We have to know that we've got a disk. This would have been a different value with a sphere or something with a different moment of inertia. And then basically getting our signs right, making sure that we know that where we're losing or gaining energy. And in this case, I haven't described things in terms of work. I could have described the work of the spring force or the work of gravity. I think it is a little bit easier when we're doing energy equivalency to simply express energy in terms of a delta in position or in terms of some kind of motion, and then equate energy state to energy state as opposed to work in a direction. It's real easy to get signs wrong when you mix those. So that's why I established the datum and then said, okay, if we're going to go with our starting point is 0 for gravitational potential energy, as we roll down slope, we're going to go to a negative energy state. I could have just as easily left the initial state as unknown and established 0 as the ending state. I would have a little bit different mathematics, but would have had a positive value for starting. So that is it for this problem. We'll have one more energy conservation problem, and that will be the end of our work energy rigid body discussions. Welcome, dynamics students. Excuse me. We have a second problem in our energy balance for rigid body planar motion, and this is kind of a complement to the one that we just completed. We've got a rigid body. In this case, it's a slender bar, a rod, and it's uniform. So we can assume that its center of mass is at its geometric center here, which would be 3 feet over from the hinge at A. And it's being supported by a hinge on its left-hand side, and then by a spring, a 6 pound per foot spring, constant spring, on its right point. And that spring is attached to a little pulley that will move back and forth such that the spring is oriented vertically all the time. So translation, pun intended, even though this is a rotational motion problem, the spring force is always going to be pulling dead vertical, straight vertical. So it won't be perpendicular to the rod. It will be always vertical. So it'll be always going at a different angle to the orientation of the rod as the rod rotates. So we do have a change in position of the center of mass of the rod. So we could represent the kinetic energy of the rod in terms of a circular path change of the center of mass, position change of the center of mass, plus some kind of rigid body rotation. Or we could simply look at the rotation of the whole rod around point A and consider that to be pure rotation. They will give you equivalent equivalent results in terms of kinetic energy. It is far easier to look at this from the standpoint of a pure rotation about point A. So in that case, we will use moment of inertia of a rod, which if you are using the Hibbler 14th edition dynamics book, we have a nice table, handy table of moments of inertia in the back cover. You can also look this up on the internet or in any kind of reliable handbook. If we look at the moment of inertia of a slender rod about its center of mass, we find that it's 1/12 the mass of the rod times the entire length of the rod squared. But about the end, it's much bigger. It's only 1/3 ml squared. So in this case, our mass is going to be 50 pounds divided by gravity in feet per second squared, which gives us something on the order of 1.554 slugs. So initially we're rotating at 2 radians per second. So if we choose to represent our motion of our rod as purely rotational, but about our point of fixed point of rotation A, which is not moving, we can represent all of our kinetic energy in terms of rotation. So we can say our kinetic energy in our initial state is 1/2. We'll call it I rod end times omega squared, where omega is 2 radians per second, and then our moment of inertia of our slender rod about the end for our 1.554 slug rod, 6 feet long, is going to end up being 865 slug feet squared. So if we do slugs, a mass unit, feet squared, divided by radians per second squared, we'll end up with slug feet squared per second squared, which is going to be an energy unit, a foot-pound energy unit. So we know we've done that properly when we have the correct units. And that ends up, we can get a number for that right now. That ends up being 37.3, referring to my notes instead of calculating it on the fly. Okay, so that's basically, we have 3 components of energy at the start. Our initial energy state's going to have kinetic, spring, and gravitational, and so will our final. So we have 1 out of 6 basically determined. So what about our gravitational potential energy? So we have a choice here. We can either consider our end state to be a zero datum, so to speak, zero potential energy for gravity, or we can consider our starting. And it turns out it is, in my opinion, a little bit easier to say our starting state represents a zero gravitational potential energy. So we're going to lose gravitational potential energy as we rotate down, and we'll look at how we determine our final state, or excuse me, our final gravitational potential energy when we move over to our final energy state. So last but not least, we have our spring energy. And the spring is not neutral. When we start, it starts with a little stretch, and we know what that is, and we know what the spring constant is. So we have 1/2 times 6 pounds per foot times our initial stretch, we have a spring length of 4 feet at this initial condition with an unstretched length of 2 feet, so our stretch is 2 feet. So we'll square that 2 feet. So we have an initial spring energy of 12 foot-pounds. So if we combine these two together, we have E total initial of about 49.3 foot-pounds. Okay, so as we rotate, we're going to increase. So we'll look over at our final state. And we're going to do a second little sketch here just to make life easier. Here's point A. Here's our rod. So point B has gone from here to here. And our center of mass has moved down over a bit. And the important thing to know is we have 30 degrees. So our vertical change for our center of mass, we'll call it H, center of mass, is 3 feet times sine of 30 degrees, and that is negative. So we're going down. So if we look at our gravitational energy final, it's going to be equal to our H, our height change, elevation change of the center of mass. So for this, we're not worried about rotation. We can put all of the mass right at the mass center and move that down. So we can treat it like a particle, because it's, even though we have some rotational motion from the standpoint of the position change in gravity, it's effectively a net translation. So we end up with, we'll just call that a negative 1.5 feet. Since sine 30 is 1/2 times mg, which in this case is 50 pounds. We don't have to use slugs. So that's negative 75 foot-pounds. So we have the total energy, which was some kinetic energy, no gravitational, and a bit of spring energy that we already had in our initial state, and then we're going to add another 75 foot-pounds effectively to it, because we're going to reduce our gravitational potential energy, and so that will get divvied up amongst our KE final and our mu spring final. So our KE final is pretty easy. It's just going to be our 1/2. The moment of inertia of our rod did not change, so we're going to have our 1/2 18.65 slug feet squared. We'll call it omega final squared. And then our mu spring final, our final energy is going to include the stretch to get to this lower position. So since the spring is basically going to be going along on its little pulley, so it's always vertical, we only have to look at this additional vertical distance. So we'll have our 1/2 times 6 feet, or 6 pounds per foot. And instead of having 2 feet of stretch, we're going to end up having, in this case, we went from 4 feet to, let's write this, 4 feet plus 6 feet sine theta. Oops. That's our total length. Get my pencil back. Minus our distance that represented our unstretched length, which was 2 feet. So instead of 4 feet minus 2 feet, we have effectively 7 feet minus 2 feet. So our mu spring final is going to be 3 pounds per foot times 5 feet squared. So that's going to give us 75 foot-pounds, conveniently. So we're going to take our initial total energy of 49.3 foot-pounds. We're going to effectively lose 75 foot-pounds of gravitational potential energy, gain 75 foot-pounds of spring energy. So those two are a wash. So our entire starting energy is going to end up going into simply the kinetic energy of our ending state. That just so happened to work out that way. As it is, we could have written KE initial plus U grav initial plus U spring initial equals KE final plus U grav final plus U spring. Just algebra. No complicated equations of motion here. So to use another color, we can just populate this. 37.3 foot-pounds. This was 0. This was 12 foot-pounds. This was negative 75 foot-pounds. And this was positive 75 foot-pounds. And so all we need to do is solve for this and then use this expression to isolate our rotational velocity final. So we can say that that is going to equal our initial total energy of 49.3 foot-pounds, and solve for W final, and we end up getting 2.3 radians per second. So simple energy balance. Important points. Probably the key was, again, looking at the divvying up of kinetic energy amongst a translation of the center of mass, along a circular path versus a choice to do all rotational. So here's a case where using the parallel axis theorem to get an expression for our moment of inertia about the end, and using that instead of a combination of the moment of inertia about the center point and some expression for the translation of the center of mass, its velocity, is going to be a lot easier. We could have found a velocity for the center of mass using 3 feet and our 2 radians per second. But it was a lot easier to just have a single expression for rotational motion and use the kinetic energy from that. The rest is just simple right triangle geometry and remembering to account for the unstretched length of the spring and be calculating our spring energy based on just the squared stretch and figuring out what that is for the final and end state. So simplicity of this problem drives in a really, really important takeaway for these work energy problems. These are very, very simple and efficient options, alternatives to a kinematics approach. We could very, very well have used a kinetics approach to this, using a force from the spring, using a gravitational force, solving the kinematics of fixed point rotation, and doing a free body diagram of the rod. Absolutely. We would have taken the rod in its final 30-degree state. We would have resolved forces from the spring, forces from gravity, forces at the pivot, etc. Solve for the unknown forces in terms of the acceleration of the center of mass and the rotational acceleration. Would have been a lot of math. This was very, very simple algebra because we didn't really have to look at final and look at the motion. We only had to look at final and ending states. So whenever possible, if you have a problem where the information you're concerned with is not path dependent, always look to see if you can use a work energy or a total mechanical energy start to finish. And if you have friction in the problem, say we had some friction in that hinge, had we been able to characterize that work of friction in terms of joules per degree of rotation, we could have simply subtracted that from the total energy in the final state and still been able to use a final and ending state total mechanical energy consideration. So that is it for this mini lecture, just 2 demo problems, and this also concludes the rigid body work energy section of this dynamics course. And for some of you, this will be concluding your study of dynamics in your course. Others, you may have some sections on rigid body impulse momentum, but in general, this is a good ending point for many of you. So just to recap in a couple of sentences, the entire study of dynamics you may have had, possibly with me or another instructor. You probably started out with kinematics of a particle or a rigid body considered only at its center of mass. You added Newton's second law and applied F equals ma and time rate of change of momentum, linear and angular. If you're talking about a curved path for that particle, you looked at work energy and impulse momentum of that particle, and then moved on to literally the planar motion rigid body analogs to everything you did for a particle. For those of you going to more advanced studies, you will then pick up, notice we've only done planar rigid body motion. We could look at motion that comes out of that plane, much more complicated. A lot of the assumptions we made throughout our study of kinetics wouldn't apply. So we would have to be more concerned with everything that's going on in the z-axis, and our products of inertia would play a bigger role in looking at the time rate of change of angular momentum. But otherwise, the main points, applications of Newton's second law, are all going to be the same. both for rotation and translation. So good luck in your follow-on studies, and hope to see you again for another engineering lecture in the future.